The pursuit of understanding the universe often follows two majestic, intertwined rivers of thought. One is a river of pure form and structure, flowing through landscapes of logic where meaning is optional. The other is a river deeply carved into the bedrock of reality, fed by the springs of observation and tangible experience. These are the disciplines of mathematics and physics. While they run parallel for great distances and often exchange vital waters, their sources, their destinations, and the very nature of their currents are fundamentally distinct. This distinction is not merely academic. It is a philosophical chasm that defines how we generate knowledge about everything from the fall of an apple to the curvature of space-time. Mathematics, in its essence, is the study of consistent structures derived from a set of starting assumptions, or axioms. A mathematician operates in a realm of sublime abstraction. The symbols and terms they manipulate, be they group, manifold, set, or number, need not correspond to anything in the physical world. Their truth is not empirical, but deductive, derived solely from the internal logic of the axioms and the rules of inference. One could coherently develop an entire geometry without ever referencing spatial reality, simply by declaring, "Let there be a set of objects we call points and a collection of subsets we call lines, such that certain specified relations hold." The beauty and power of mathematics lie in this very day. Detachment. It creates perfectly tuned logical engines, ready to be fueled by any content that fits their formal requirements. This drive for generality is a hallmark of the mathematical mind. Why solve a problem in 3 dimensions when one can solve it in times n times dimensions? The times n asterisk dimensional proof is more elegant, more powerful, and encapsulates a universe of specific cases within a single sweeping statement. The mathematician's triumph is to create a master key that can, in principle, open an infinite number of doors, even if many of those doors lead to rooms with no obvious physical analog. Their work is guided by an internal compass of rigor, consistency, and aesthetic elegance. Physics, however, is anchored to a specific, stubborn reality. The physicist is not interested in all possible universes that could be logically constructed, but in this one particular universe we inhabit. While they borrow the logical engines forged by mathematicians, they must fill those engines with specific fuel, quantities that have empirical meaning. For a physicist, the symbol times m times is not just a variable. It means mass, the measure of inertia observed when pushing a cart, the source of gravitational attraction that holds planets in orbit. The symbol F represents force, the tug of a rope, the push of a hand, the pull of a magnet. Consequently, the physicist is often profoundly interested in the special case, particularly the case of 3 spatial dimensions and 1 time dimension. When a mathematician presents a glorious theorem for times n asterisk dimensional space, the physicist's immediate thought is, what happens when times n equals 4 times for space-time, or even just times n equals 3 asterisk? This specialization is not a lack of imagination, it is a necessary focus. The physicist's reasoning is guided not only by mathematical rigor, but also by a seat-of-the-pants intuition about how the world behaves, a gut feeling for dynamics, honed by a lifetime of implicit observation. This intuition acts as a crucial guide, suggesting which mathematical paths are fruitful and which are likely dead ends in describing nature. The translation process from physical intuition to mathematical formalism and back is where the gap between the disciplines becomes most evident. A physicist observes the rhythmic swing of a pendulum and senses the interplay of gravity, inertia, and constraint. They then map these sensations onto differential equations. The mathematician can take those same equations and analyze their properties, finding symmetries, stability conditions, and general solutions, without ever thinking about clocks, weights, or gravity. The physicist, however, must constantly cross the bridge back to reality, interpreting the solution to mean the period increases with the square root of the length, a testable statement about metal bobs and strings. This difference in focus leads to a different relationship with precision. For a mathematician, absolute rigor is paramount. Every step must be justified, every edge case considered. In physics, however, such exhaustive rigor can sometimes be an obstacle to progress. The real world is messy. and its fundamental laws are often glimpsed first through approximations and idealized models. A physicist might happily neglect air resistance to understand the core principle of projectile motion, or treat a complex planet as a point mass to grasp gravitational law. Insisting on perfect mathematical completeness from the outset could paralyze discovery. As one might say, the physicist needs to be precise enough to be correct, but not so obsessed with precision that they lose sight of the phenomenon itself. It is vital to understand that this is not a critique of either field. Mathematics is not a slave to physics. It is a free and sovereign kingdom of the mind. Mathematicians have every right to explore structures motivated solely by their internal beauty and logic, with no concern for utility. The history of science is littered with examples of useless mathematics, non-Euclidean geometry, matrix algebra, group theory that decades or centuries later provided the perfect language for a physical theory. Physics is one of mathematics' most demanding and inspirational clients, but not its only patron. Ultimately, the synergy between the two fields is what makes modern science possible. Physics poses concrete, meaningful questions about reality. Mathematics provides a vast toolkit of abstract structures with which to frame answers. But the physicist must always perform the final, crucial act of interpretation, tethering the abstract symbols back to measurable quantities, to the click of a Geiger counter, the streak of a particle in a cloud chamber, or the redshift of a distant galaxy. Without mathematics, physics would be a collection of incoherent observations. Without physics, a great deal of mathematics would be an orphaned game, beautiful but untethered. The relationship is thus a dynamic dialogue between meaning and form, between the concrete and the general. To confuse the two is to misunderstand the nature of both. Appreciating their distinct domains, one dedicated to the architecture of reasoning itself, the other to the application of that reasoning to the tangible cosmos, is the first step toward grasping the profound partnership that has unlocked so many secrets of the universe. They are not the same river, but together they water the entire landscape of human understanding. Yet, this enduring partnership thrives precisely because of the tension at its heart. It is a creative friction. The physicist, grounded in the concrete, constantly demands of the mathematician, "Can your structure describe this?" In doing so, they stretch and stress the mathematical fabric, sometimes revealing flaws or inspiring new branches of thought. Conversely, the mathematician, in their free exploration, occasionally hands the physicist a tool of such power and readiness, like the tensor calculus that Einstein used to formulate general relativity, that it feels less like an invention and more like a discovery of the universe's native tongue. This cyclical dance from the physicist's concrete question to the mathematician's abstract exploration and back to a new, deeper physical understanding is the engine of fundamental discovery. It reminds us that our quest to comprehend reality is not a single-threaded path, but a constant, dynamic negotiation between the world as we experience it and the boundless landscapes of logic we can conceive. To stand at this intersection, respecting both the anchor of meaning and the wings of abstraction, is to hold the master key to the scientific endeavor.